So good afternoon, everyone. So I will be telling you about clusters of galaxies, and so far you have, I suppose, heard in general about radio astronomy and how the sky looks in radio as compared to what we see with our naked eyes, and in general about galaxies, etc. So clusters of galaxies are just special locations in our universe, and this special location basically influences the properties of the galaxies that happen to be there. And it not only affects the galaxies, but basically the whole system consisting of even the thin gas surrounding the galaxies and the galaxies themselves. So we'll go through the various phenomena that happen in these systems. So I would like to start by showing you this large-scale structure of the universe. This is basically a slice of our universe as seen by an optical telescope. So basically these points here, reddish and green, the ones going through this color scale, are basically each of these dot is a galaxy, and we are basically sitting here and looking far away into the universe. So this redshift is shown along these axes. So imagine that you are standing here and you are having a look at this slice of sort of a angular sector, and you actually know the distances to these points because you have measured the redshift, and you can tell where they are. So if you put together all these points in such a plot, what is remarkable is that to our eye we can make out that the stars are distributed all across the sky, and they don't look really, meaning we have made constellations and things like that for our own reference positions in sky. But when you look at it in this is essentially a 3D picture, and what is seen is that these are not uniformly distributed. So if you consider galaxies, they are not just randomly distributed across the space in the universe, but they seem to be forming these groups and structures where they are densely populated, and there are structures where they are not. So this is basically referred to as the large scale structure of the universe. And this this structure basically forming of filamentary filaments like structures, and then these voids, they are the components of the large scale structure. Now one other remarkable thing seen in this picture made with the Sloan telescope is that this color scale basically is it's a G minus R. So these are optical filters, G and R, and you can take the difference, which is called color. So in astronomy, when you take the difference between these optical magnitudes, you get what is called as color. And what you can see here is that immediately you can make out that the reddish points somehow seem to be at the locations where there seems to be more grouping as compared to the greenish blue points, which seem to be scattered in locations where there aren't many red points. So this already tells us some story that when galaxies cluster together, something happens to them which makes them emit more red light than bluish green light. So we will come to these aspects when we talk about clusters of galaxies. So what I showed you just now was actually a picture taken by telescopes and then constructing a 3D picture because we know the redshifts. Now, what do the simulations tell us? So we know that most of the universe is made up of dark matter. So what in these simulations, what was done was that you take a very large number of dark matter particles and just allow them to fall under gravity and check how they finally look after you evolve this system for the time scale of the age of our universe. And what was seen in this millennium simulation was that it forms a web-like structure, and in particular these nodes of this web are very massive systems which are called galaxy clusters. So this is one massive system zoomed in here, and all these brightened particles are actually just like galaxies, and they are basically all clustering together in these nodes where there is more mass, and it keeps on attracting more mass and they grow. So this picture shown by simulations, if you just consider dark matter and gravity, hasn't changed much. You can put in gas and basically baryonic physics in it, because there you'll have to account for the radiation and all the other electromagnetic effects. Whereas dark matter, as we know it, uh, only responds to gravity, and basically gravity already has shown you that most of the structure in the universe can be formed with just the gravitational force driving these particles. So the coming to the scales that we are going to talk about in our discussion about galaxy clusters. So typical size of a galaxy cluster can be said 1 megaparsec or so. And what is this megaparsec? Probably you all have come across it, or you have read it on your own at some point, I suppose. So you know that parsec is a unit of distance used in astronomy quite commonly, apart from light years. And parsec is actually 3.26 light years, and to compare it, sun to earth distance, which is called 1 astronomical unit, is actually, if you express it in parsec, it is 5 times basically a 5 microparsec. Now what we are talking of when we talk of galaxy clusters are systems which are on the scales of a megaparsec. So you can see the enormous range of scales, the difference starting from our Sun-Earth system to galaxy clusters. So these are really huge systems. In fact, these are the largest gravitationally bound systems in the universe that we know of, and they are constantly evolving. And these are also the youngest objects in the universe, because they're still forming. So the way this large scale structure is believed to have formed is that smaller structures formed first, and then they merged together and have been evolving into larger and larger systems. So that is how galaxy clusters have come into being, and they are still growing. So in this talk, what I'll tell you about is what are the main constituents of galaxy clusters. And then we will review as to how we came to know of all these components, because not that people knew of all the components already way back when astronomy was only limited to optical studies, but they gave very profound inputs and from or deductions from optical studies, which allowed all the progress that was made once other bands were accessible to astronomers. And then we will talk about the speciality of galaxies in galaxy clusters as compared to field galaxies. And then I'll talk about the intra-cluster medium, because in galaxy clusters, not only the huge dark matter attracts galaxies or it keeps them bound, but it also has can hold a huge reservoir of diffuse gas, which is called intra-cluster medium. I'll talk about the radiation mechanisms that govern the emission that we actually detect. And I'll talk about Sunyaev-Zeldovich effect, and then come to what we actually see in radio bands. And then even clusters are not let's say the youngest objects, probably superclusters, which are the systems of galaxy clusters themselves. So galaxy clusters themselves are still merging, and they're forming even larger structures, and these are called superclusters. So we'll come to that towards the end. So I'll first tell you about what are the components of galaxy clusters that we know today. So galaxy clusters were initially identified as regions of overdensities in the projected distribution of the optically known galaxies. So earlier studies were usually limited to basically once photographs could be taken of the sky, people studied the objects detected in these photographs, and then identified such regions where they found that lots of galaxies, like objects, or lots of objects are clustered in certain regions, and they called them as galaxy clusters. So today we know that galaxy clusters are these huge systems of galaxy of huge masses of the order of 10 to 14 to 10 to 15 solar masses. They contain hundreds, thousands of galaxies, and these are all confined in regions of about a megaparsec or so. And the velocity dispersion, so if you measure, so these galaxies are not just standing there, they are just like our solar system, everything is moving, and in our galaxy things are moving. These galaxies are moving in orbits decided by the gravitational potential of the galaxy cluster. And if you measure the velocity dispersion of these galaxies, it comes out to be about 1,000 kilometers per second. So these galaxies are moving really fast in this cluster potential, and that and the galaxy clusters also contain this diffuse gas. So apart from galaxies, there is a huge amount of gas surrounding these galaxies. So in this picture here, you see that one of them is basically a galaxy, the same galaxy cluster in optical and X-rays is being blinked. So if you looked at this patch of sky, in optical you will detect all these bright galaxies. If you look at it in X-rays, you will detect this huge blob, which is basically the intra-cluster medium. So the intra-cluster medium is extremely hot gas at the center of the cluster, and the luminosity, X-ray luminosities are of the order of 10 to 44 to 10 to 45 ergs per second. So the different bands actually give us a very different picture of the galaxy cluster, and all these together help us understand this physical system. So what we also know is that most of this mass, whatever this 10 to 14 to 10 to 15 solar masses that one galaxy cluster contains, is most of it is actually dark matter, and only about 15%, 10 to 15% is actually baryonic matter. And among the baryonic matter, most of it is actually hot gas or the plasma, and only a few percent is in galaxies. So this is a rough mass distribution of the mass in a galaxy cluster among its components. So most of it is actually dark matter, and that is where most of the gravity is coming, or is being, basically the gravitational potential is due to the dark matter, most of it. And these galaxies moving at such high speeds can be basically contained into these volumes because of this very strong gravity. So here I want to give you an overview of, so we will be talking about, so next after these introduction, that what are the constituents, we will be talking about the physical properties of this system, because our interest is to learn the physical phenomena in this system. So I want you to look at, basically this chart is showing you comparison of the particle densities in the various plasma or various media that we know of, the range of magnetic fields that are there in these media, and the mean free path. So these physical parameters are very important for us to understand the state of these systems. So for example, if you consider Earth's ionosphere, the particle densities there are of the order of 10 to 4 per centimeter cube. The magnetic field roughly a third of Gauss, and the mean free path in centimeters is of the order of 10 to 6. If you consider solar corona, it is a more thin medium, it is a thinner medium. It's basically it has a weak magnetic field, and you can see that I think here I have interchanged the particle density number, but the mean free path there is much larger. Now going directly to interstellar medium like spaces, basically let's say the Milky Way interstellar medium, the particle densities are very low. The magnetic field is of the order of a micro Gauss or so, and the mean free paths are now of the order of this 10 is to 15 centimeters. You can compare this with the number for a parsec, 10 is to 18 centimeters. So this is really going very large. Basically, mean free path, basically you can imagine that, okay, what is the largest path that a particle travels before it collides another one. So the particles are really particles really have to go really long distances to meet another particle. So it's very, very thin space. There's nothing, basically, essentially there is nothing there, one can say, in comparison to what we are used to on Earth. And going to this intergalactic medium, so if you go all the way outside Milky Way and start to look at the space between two galaxies, the densities there are very low, and even the magnetic fields are very low, and the mean free path is extremely large. So these basic parameters define how the physical system evolves. So to just give you an idea, people talk of thermal systems in equilibrium. So people are basically referring to such systems when there is a lot of exchange of energies between the particles. So any system, if it is in equilibrium and if you try to disturb it and if it's a stable equilibrium, it will try to come back to its equilibrium state. And the way it comes back is basically by exchanging energies between the particles. And that happens via phenomena which allow particles to exchange energy. And this can happen by direct collisions. This can happen through electromagnetic forces. So here you can see that these spaces are so sparse that making these changes really happens on very long time scales. So this intra-cluster medium, it is, although it is very thin, it is still a very huge system. So just like we can detect the neutral hydrogen line because of the just sheer number of the hydrogen atoms that are present in our universe. Similarly, these systems are very large, and although this plasma is very thin, there is so much of it that we still do detect it with our telescopes. So this intracluster medium is basically diffuse gas which pervades the space between the galaxies in a galaxy cluster. And this is mainly a thermal plasma. Now this thermal means basically that the emission mechanism involves phenomena which depend on the interaction between two particles. So here the particles that are interacting are basically charged particles. These are electrons and protons, and mainly electrons basically. The electron densities are of the order of 0.1 to 10 to minus 3 centimeter cube at in these systems. The temperatures are of the order of 10 to 8 Kelvin, and most of this the thermal plasma is visible and detectable to us in X-rays. And the mechanism which is allowing that is thermal Bremsstrahlung. So maybe in some other lecture you have heard this term thermal Bremsstrahlung. Basically, it's the radiation mechanism. It's a radiation which happens when there is acceleration of two charges near each other. So it is also known as free emission. So two free charges, when they come close and interact, you will come across something called as thermal Bremsstrahlung. Now, what is quite invisible in this X-ray view of galaxy clusters or even the optical view of galaxy clusters is the presence of relativistic particles or the cosmic rays and magnetic fields. So we did come to know of these components in the intracluster medium, and these are not detectable in most observing bands. However, you may have heard of synchrotron radiation. So when electrons, relativistic charged particles move in magnetic fields, you come across something called as synchrotron radiation. So when charges are accelerating in presence of a magnetic field, we get synchrotron radiation. And this is what allows us to infer that the intercluster medium contains relativistic electrons and magnetic fields. And this is where the radio observations play a crucial role because they are the direct probe of these components which are otherwise invisible. So as I said, intra-cluster medium, whatever name we give it, it is finally for a physicist, this is a plasma. And we want to learn the properties of this plasma and try to see what sort of phenomena can occur in this plasma. So here I will just tell you very briefly about the plasma properties of the intracluster medium, just like the mean free path, etc. This is a plasma, so you also have these properties in a plasma. So some of you may have come across it, or eventually in your courses as you go through your uh, further years of your study, you will definitely come across plasma physics. Um, so here, if we take these standard parameters like electron density of 0.01 per centimeter cube, temperature of about 5 keV. So I have been expressing temperature as well in keV. Often in galaxy clusters, you will see that people say that the temperature of a galaxy cluster is so and so keV. So of course, Kelvin is the unit of temperature, but what people often refer to in astronomy is this KT expressed in units of keV. And let's say that is a typical galaxy cluster of few keV and a microcosm of magnetic field. So one can check what are the different properties, the mean free path of these charged particles in the plasma. And because this is a plasma, there are some other important properties like the Debye length, the electron skin depth. In the context of synchron radiation, or when there are charged particles moving in magnetic fields, there is the Larmor radius. So what we find for a plasma with these properties is that the mean free path. So there are all these values given in this table, and also expressed it in units of this femtoparsec, or nanoparsec, etc. has been also expressed in units of kilometers here and megameters, for you to imagine what kind of distances these are. So two parameters are very striking here. Sorry. One is this mean free path. So the mean free path comes out to be, a kiloparsec, which is very long distance for any particle to go before meeting any other particle. And the electron Larmor radius. So the electron Larmor radius is, if you compare the two numbers, electron Larmor radius with the mean free path, you can see that the Larmor radius is much smaller than the mean free path. So what particles or these charged particles are doing in this plasma is that if they are in this weak magnetic fields, they are essentially tied to these magnetic fields and just moving along the magnetic field lines. And really there is nothing else to disturb them. So they will meet another particle in a kiloparsec. So really their motion is governed by these very weak magnetic fields, because the mean free path is so large. So this comparison tells us already that in such a plasma, your physical phenomena are going to be governed to a large extent by this very weak magnetic field, because the particles are going to follow the magnetic field. So that is one aspect of this medium, and this is also important for radio astronomy. Therefore, I have emphasized it a little bit over here. So now one question is, now we'll move on to the various things, various properties of galaxy clusters, etc. Regarding the galaxies, etc. But then why are we studying galaxy clusters? So I have just listed a few. There are many motivations why one would like to study galaxy clusters. So first of all, these are most massive laboratories. So if we are to study new phenomena in physical conditions which are not possible for us to create on Earth or anywhere else in the universe, these are our laboratories. And if we are to study dark matter, even these are dark matter dominated, gravitation is basically mostly dominated, the dark matter dominates in terms of its just presence of 80 to 85% in mass, in these systems. So these are definitely new laboratories for anyone trying to study new phenomena. These are also probes of structure formation. People study the sizes of galaxy clusters of a large number of them across the sky and come up with cosmological parameters based on this, because they give us an idea about how the universe has evolved or to which stage has the evolution reached in the universe. These are also most massive reservoirs of baryons. So this intra-cluster medium is the most massive reservoir of baryons that you can find in the universe. These are also probes of large-scale magnetic fields. So actually studying magnetic fields on astronomical scales, like even the scales of galaxies or on even larger scale on intergalactic scales, the presence of these intra-cluster medium and intergalactic medium, the charges in these media are allowing us to probe them on the very largest scales possible in the universe. These are also host to the most massive galaxies in the universe. So this system basically provides a special incubation region in the universe. Sorry, excuse me. That allows the galaxies to grow to really massive sizes. Just 1 second. So one other thing about galaxy clusters is that they are basically record keepers of nucleosynthesis in the universe. So if you study the distribution of elements in the galaxy clusters, they can give you another basically a probe for how the different elements have formed in the universe. So there is enough motivation and to study galaxy clusters, and these properties will tell us about the universe as a whole. So to go back a little bit, how did it all begin? So as I said, these were first identified as optical, basically overdensities of objects detected in optical images of the sky. So in fact, this was already noticed way back in 1902, and this was the first galaxy cluster to be identified, which was named the Coma cluster. This is the most massive nearby cluster uh, at a distance of about 100 megaparsec from us. And as you can see, this is an optical image of this galaxy cluster, and it shows presence of uh, very bright elliptical galaxies mainly, and lots of other smaller galaxies as well. So if you look at this same cluster in X-ray and radio bands, this is what it shows. So here there in the background there is also the optical image. So if you go back, you can see these two major galaxies. In this next picture, you can see these two major galaxies over here, and this is the, in color you can see the X-ray image. Sorry, the radio is not overlaid over here. So starting from Coma and galaxy clusters in general, there was very interesting implication of these systems that that was first noticed by Zwicky. So the existence of dark matter itself was basically proposed based on the observations of the velocity dispersion measurements of galaxies in the Coma cluster. So this is a very interesting paper actually. It's available in English and you can also try to read it. The argument is based on the virial theorem, and the basically what was seen was that the velocity dispersion of the galaxies was measured for the Coma cluster. And if you put together, now we are seeing only galaxies there. So what one would assume that the mass in this system is likely to be just the sum of the masses of these galaxies that are visible. Now, if that sort of a mass were to support or or gravitationally bind this sort of galaxies moving at such high speeds, that led to a contradiction, and that is where the proposition that there must be additional mass that we are not able to detect in terms of the just the light that is emitted from these galaxies. So this existence of dark matter was actually implied by the measurements of towards the galaxies of Coma cluster system. I will also briefly mention another additional another discovery by Zwicky, proposed by Zwicky, which was the phenomenon of gravitational lensing. So if so in this picture it is illustrated as basically if you are looking at a certain direction in sky and along your line of sight there is this galaxy cluster and you are looking actually at the object which is at a very large distance from you, even beyond this galaxy cluster, then the light from this object will be affected by the gravity of this intervening cluster, and what you will see or what is the apparent picture of that region of sky is that you will see the image of this galaxy smeared into this kind of arcs, and this is due to gravitational lensing. And such spectacular system, for example here shown by the Hubble Space Telescope, um, is shown here, where you almost see a full ring depending on the orientation of the background object and the intervening matter. You will see differences in the type of the distorted images that you will get of this background object. So galaxy clusters are such massive systems capable of distorting the images of distant objects, and those can be used to our advantage because there is also a magnification involved. But I will not go into that direction, but definitely this is one important aspect of galaxy clusters which people study and use it in fact to map the mass distribution in galaxy clusters. So these are other examples of gravitational lensing. So these are two clusters, and in the optical images you can see that everything looks like there is a very common presence of these arcs, which is due to this distortion introduced by the gravitational lensing. So coming to galaxies and galaxy clusters, you may have come across this Hubble's classification scheme of different galaxies. And in galaxy clusters, what you will come across are mainly elliptical galaxies and S0 galaxies, as compared to the fraction of spirals and other barred spirals, etc. So any picture of galaxy cluster, you will immediately notice that you are seeing a large number of elliptical galaxies. So we will come to that in a couple of slides. So in any galaxy cluster, what is very striking is the presence of this large brightest cluster galaxy that is residing at the center of these galaxy clusters. So these are called brightest cluster galaxies, and these are, so if you consider all the galaxies in the universe, the galaxies residing at the centers of galaxy clusters are brightest galaxies among all galaxies. So one interesting thing which was studied regarding galaxies and their environments is this famous plot by Dressler. There are many revised versions of this from more recent studies, but this picture essentially remains true. So what is plotted on y-axis is the fraction of galaxy populations. On x-axis is the projected density. So as you go to the right on x-axis, what you will find is that the fraction of elliptical galaxies is rising. The fraction of S0 galaxies is also rising, and but the population of spirals and irregular galaxies are falling down. So in these regions, which are mostly densities nearing the type of galaxy cluster like objects, one can see that the fraction of elliptical and S0 galaxies is very high as compared to the other galaxies. And basically this strongly implies a link between the type of the galaxy and the environment. So definitely the environment must be doing something to the galaxies in order for them to uh, become elliptical or S-zeros, and something is happening to spirals that they are disappearing as they go into high density environments. So these brightest cluster galaxies are really large. They are larger than even typical elliptical galaxies. They are of the sizes of 5 to 100 kiloparsec, including their halos. They have very high velocity dispersion. So as such, the galaxy itself is nearly at rest because it is at the deepest point in the gravitational potential. But the stellar velocity dispersion can be quite high. There is a large fraction of dark matter. It has different fundamental plane projections. So this I will not go into. Maybe you have heard of the fundamental plane in some other talk. They are also more likely to be radio loud. So a lot of these cluster center galaxies are very bright in radio. So it seems that the BCGs are very special galaxies and their environments are making them special. So these environments are basically um, of the order of 100 galaxies per megaparsec cube as compared to less than 10 galaxies per megaparsec cube for galaxies residing outside clusters. So this is another property showing the extent of brightest cluster galaxies. They are also called CD galaxies. So these CD galaxies are basically, so this is surface brightness, magnitudes per arc second square, and this is the radius. So from the center of the galaxy to outskirts. If you plot a profile of surface brightness, you'll see that the surface brightness profile follows this curve. Whereas for these giant galaxies in galaxy clusters, at the centers of galaxy clusters, this curve basically flattens out and there is another envelope which is called the extended halo of the galaxy, and this is basically one of the characteristic of these brightest galaxies. So this evolution is made possible by the special environment that they reside in. So galaxy clusters are, as I showed you, they are at the nodes of these intersecting filaments of the large scale structure in the universe. So so how did this happen? It didn't happen as sort of spontaneously, but it happened as the evolution of the universe has been taking place. So galaxy clusters have been sites where there was more mass, and it attracted even more mass and grew to this extent of a galaxy cluster at this epoch. So the same thing happens to the galaxies. So these galaxies happen to be in this very special place where there is a lot of mass surrounding them, and they can have the time to basically attract this mass and evolve into very large galaxies. So this is one simulations. So through simulations also people have understood that the location of being in an environment where there is a lot of mass surrounding you allows you to grow to these sizes like the brightest cluster galaxies. So now that was about galaxies, but what about the intra-cluster medium X-rays? So earlier, basically X-rays are not visible from the surface of the Earth because of our atmosphere. So until really some techniques came about, like sending experiments attached to balloons in the high altitudes in the atmosphere or up to satellites, one did not have an X-ray view of the universe. So this happened in late 60s and in the 60s and 70s when the first satellites or the observatories were sent. So earlier people were confused as to what is this blobby X-ray emission that we find. So towards Coma has been a big cluster and it is nearby also. So it has been a test bed for many issues regarding galaxy clusters. So there was detection of diffuse X-rays from Coma cluster, and at that time it was not clear what was the physical mechanism. So in 1966 it was first proposed that this was actually thermal bremsstrahlung based on the X-ray properties, and this mechanism of free emission was considered to be the most viable mechanism which explained all the properties that were measured for this X-ray emission. And then they predicted the temperatures of about 10 to 8 Kelvin or so in such systems. And these have been now, until today, there have been many missions like Chandra X-ray telescope, the XMM Newton X-ray observatory, and now basically Chandra is still operational. It was launched in around 2000 and it is still operational. And the one recent which showed a very detailed picture of galaxy cluster, which was the Hitomi mission. Unfortunately, after it took its commissioning observations, it had a problem, and then basically the satellite did not survive. So the observatory is gone, but the commissioning data that it had taken has provided very sensitive measurements of the spectrum of the intracluster medium plasma. And at this very high temperatures, you know that even the iron is basically ionized, and in that state, it has a transition, which is this 7 kV line, and this has been measured very precisely by Hitomi telescope, and it has given an idea of the turbulence in the intracluster medium. So starting from finding that this was thermal bremsstrahlung emission to measuring really the turbulent broadening in these lines, that is the path that is the extent of detail that we have come to from the first detections in X-rays of these intracluster medium. So there has been the Rosat mission, which has taken basically a picture of the whole sky in X-rays, and that was the mission which resulted in the detection of many thousands of galaxy clusters in X-ray bands, and that really paved a way of studying the galaxy clusters statistically, the intracluster medium. Earlier clusters were of course known from optical surveys, but this gave a good idea of the presence of intracluster medium and its properties. So this is luminosity versus redshift plotted for the clusters detected by the Rosat mission, and you can see that a large number of clusters are detected in the nearby region as compared to very high redshift, because these would be fainter at high redshift. So what is this thermal bremsstrahlung? So if you look at the formula for emissivity, you see that there is a very strong dependence on the square of the density. So what happens is that the X-ray image that you see, you are measuring the flux in X-rays, and this flux is basically proportional. Basically, this emissivity is deciding what is the flux, and the square of the density basically makes it very difficult to detect any emission from the outskirts of galaxy clusters, because the density of the particles, so the electrons, is going down very fast, and only the centers of the clusters are very bright, and as you go away, as the density falls, so does the emissivity, and thus you cannot detect the cluster beyond a certain point. So in astronomy, as you know, any emission by particles, any emission of energy through any radiation mechanism by particles, we refer to it as cooling. So the particles are losing energy. So these electrons are also losing energy via thermal bremsstrahlung, and the time scale over which they lose the energy is this cooling time scale, and this time scale tends to be very long. So if you consider typical cluster temperature and the density, the time scale comes out to be of the order of a few giga-years. So this is a very long time scale, and thus this plasma is unlikely to cool very fast. However, it is shorter than the time scale of the universe. So one would expect that if this gas just loses energy on this time scale, it can start to basically clump together, form stars, etc. So there was the proposition that this cooling should lead to accumulation of cool gas at the cluster core, and then there should be a runaway cooling. And then if such cooling happens, then this cool gas can even just form very dense clouds and start to form stars. And it was expected that if this were happening, one would see the centers of galaxy clusters to be very bright, and producing stars at extremely large rates. However, there was no evidence for this cool gas, and actually Chandra and XMM Newton satellites, X-ray observatories, solved this so-called cooling problem. So there is something which is keeping the gas at the cluster cores from cooling. So if you leave it and we don't consider any other physical effect, it should cool and form stars, but that is not happening. So we are still missing whatever else is happening in the clusters. So that is where the role of feedback has been very important. So you know that the brightest cluster galaxies are at the cluster centers. So they also contain these supermassive black holes, and they can accrete and produce jets, which you can see as radio galaxies. So here there are a couple of clusters shown with the radio emission from these galaxies in the form of jets and lobes. And you can see that they really, these jets flow through the intra-cluster medium, and um, these jets form cavities in X-rays. So basically this activity of the supermassive black hole can prevent this runaway cooling in the surrounding gas. Although this issue of whether feedback is enough to offset the cooling is still a debate, and people are doing observations and trying to learn how the interaction between the non-thermal, these galaxy jets and lobes and the intracluster medium offsets how does it offset the cooling. There is another important aspect where there is a transformation of galaxies. So as I showed you earlier, the Dressler's plot, where the galaxy type and the environment seem to be very closely connected. So the galaxies are basically falling under gravity, and in this, if they are falling into a cluster, uh, let's say a spiral galaxy is falling into a cluster, what will happen? So there is this dense gas, and it is moving at a high speed through this surrounding gas. So the loosely bound gas in this spiral galaxy gets stripped off, and there is this jellyfish galaxy shown here. So this particular galaxy is moving towards the cluster center, which is in that direction. And this beautiful optical image is showing you this trail of stars and gas left behind by this galaxy as it is falling towards the cluster. So these galaxies basically lose most of their gas and the blue stars, and when they end up as members of the cluster, they are these red galaxies, mostly with dead stars and essentially no gas. So the discovery of jellyfish galaxies is really telling you that there is this transition population of galaxies when they fall in the clusters. So this effect of stripping not only happens it is detectable in optical, but this also happens through the jets of galaxies. So there are different galaxies in galaxy clusters which can basically have radio jets, and depending on how the galaxy is moving through the surrounding medium, these jets can bend, and that is what these bent radio galaxies are allowing us to probe. So there are galaxies called the head-tail galaxies, where the jets are very bent, and you can basically learn about the medium that surrounds them. So coming to another aspect, so about the detection of galaxy clusters through their effect on the cosmic microwave background radiation. So I suppose all of you have sometime heard about cosmic microwave background. So this is a perfect black body radiation, or a near perfect black body radiation coming from all directions in our universe. So whichever direction you look and measure, you will find this beautiful black body. If you measure in the right wavelength band, you can measure this black body radiation. And this is a background to everything that we observe in the universe. So now, what happens if we look at the cosmic microwave background radiation in a direction where there is no galaxy cluster along the line of sight, and in another direction where there is this intra-cluster medium intervening our line of sight. And what if we measure the spectrum of the black body? Is there a difference? So this is what was measured, was proposed actually earlier and then measured. So these CMB photons, so these are microwave background photons, which are upscattered by the electrons in the ICM, and therefore in the spectrum they will lead to a decrement in the at the low frequencies and increment at high frequencies, because they will basically upscatter these photons and they will appear as a high frequency population. So if you measure the spectrum of along a line of sight where there is a cluster, you will find that this perfect black body spectrum is actually distorted, and this measurement of distortion can allow you to infer the properties of the intracluster medium. So this is called Sunyaev-Zeldovich effect. It was proposed in 1972 and then soon verified with observations. So so basically if you take the difference and then plot just the difference, you will find that in the low frequency range you have a decrement, and in the high frequency range you have an increment. And this property is proportional to the total gas pressure in the intracluster medium. So it's a very sensitive probe of the intracluster medium pressure. So these were these first detections of this effect happened in early 80s, and now there are several observatories like the Atacama Cosmology Telescope, the South Pole Telescope, and the satellite observatory, the Planck satellite, that are mapping the entire universe in these bands. So this allowed us to make pressure profiles of intracluster medium, and these are very sensitive probes of measuring of mass, basically measuring the total mass, to give you an idea of how much the picture has been has changed. So until the 80s, people were still detecting the Sunyaev-Zeldovich effect, and with the advent of Planck satellite, there is an all-sky measurement of the Sunyaev-Zeldovich effect essentially across the sky, and one detected many new clusters. So earlier I had showed you this plot of luminosity versus redshift from the Rosat X-ray satellite. As compared to this, now our picture has come to this plot. This is a reasonably recent picture after the galaxy cluster catalogs using Sunyaev-Zeldovich effect have been released from the Planck, SPT, and ACT collaborations. So these all these clusters are now detected using this Sunyaev-Zeldovich effect. So even those clusters which were not earlier detected by X-ray missions are now are detected.
Could you mute your mic? Mics on. Carry on, Ruta.
Yeah. So our picture of how many galaxy clusters are known in the universe, etc., has drastically changed really in the last few years when the new detections through Sunyaev-Zeldovich effect have become available. So there is a huge number of clusters available to do statistics and learn about the pressure profiles and the properties of the intracluster medium. Now, at the end, I want to come to clusters in radio bands. I think I'll take a few more minutes. I hope that is okay. So, so basically in radio bands, I already mentioned that the synchrotron emission from the relativistic electrons and the weak magnetic fields in the intracluster medium, that happens to be detectable in radio bands, and that is where our interferometric observations have come to our aid to learn about the radio properties of the galaxy clusters. So in what we see in radio towards a galaxy cluster is a mix of two things. One, that we will definitely detect the various jets and lobes of radio galaxies of the radio galaxies in the cluster. But apart from that, there is this diffuse emission. So in this picture, the color scale is showing you the X-ray emission. It's a blob, the intracluster medium as detected in X-rays, and these contours are showing you the radio emission. So here all the contributions from individual radio galaxies or background or foreground point sources has been removed. So what you can see is this diffuse emission which pervades, basically is associated with the entire intracluster medium itself. So there is this weak magnetic field and relativistic electrons in the intracluster medium, which is making this source called radio halo. So these are sources of very large sizes. They can even be a couple of megaparsec also, few megaparsec in some cases. Like this one is one of the largest radio halos known, and they are radio bright radio diffuse radio sources towards galaxy clusters. And so far many theories have been proposed regarding the origin of these sources, such as so basically you want a physical explanation as to how these relativistic electrons and magnetic fields are produced in these galaxy clusters, or how are they sustained and lead to these sources. So there is no satisfactory explanation of these sources so far, and we are actually on that mission to find out the origin of these sources. There are even other radio sources in galaxy clusters called the radio relics. So galaxy clusters, as I said, are still growing entities. They are accreting mass and growing gradually. But sometimes what happens is that this growth suddenly happens because, let's say, two massive clusters themselves come close to each other, and there is what is called as cluster merger that happens. And these kind of violent merging events can lead to shocks in the intracluster medium. And in these two pictures here, in the lower picture, the green emission is actually the radio image of the cluster Abell 3376, and this red thing here is the intracluster medium. So there is a merger of two clusters happening in this direction, and you can trace the outgoing shocks in the form of radio emission, because at shocks electrons can be reaccelerated, and what you get is relativistic electrons, and there is due to the compression you also have amplification of magnetic fields, and this leads to these spectacular arc-like sources. Here in this other picture, the blue one is actually X-rays and this red is radio emission. So these arcs can give you a very beautiful picture of the shocks in the galaxy cluster mergers. So merging clusters are actually, you may have come across two body collisions, and it's the same problem here. So there is an impact parameter, and imagine these two sort of spherical objects colliding. But here I will just quickly tell you about the difference between a collision of two objects and two galaxy clusters. So galaxy clusters are not just rigid spheres; they are basically this huge amount of dark matter, the intracluster medium, and these yellow dots signifying the galaxies. Now, so these three components behave slightly differently in the way the collision, as the collision progresses, because of their different properties. So, as you know, dark matter essentially just obeys, is just affected by gravity, and that will take over. So, let's say these two clusters are merging. So the galaxy, the dark matter basically just passes through each other. So there is this huge cluster on the top, and here there is a smaller subcluster. If they merge in this direction, what you'll end up is that they will pass each other, and then according to the gravitational pull, they will again, come back and cross each other again, and then merge eventually. What is happening is that the galaxies also follow mostly the properties of dark matter. So the galaxies are very spaced out in galaxy clusters. So there is no direct impact of one galaxy on another in a collision. So galaxy cluster mergers, basically these are just point particles floating or just moving around in this dark matter potential, and they also just go according to gravity. So they follow mostly the dark matter course, and you will see that the galaxies and dark matter cores are following each other. However, the intracluster medium clouds, they are not just being affected by gravity, but there are these electromagnetic forces And because of the magnetic fields and the tie-up of the particles and magnetic field motions, you have these weakly collisional plasmas, leading to shocks and turbulence in the intercluster medium. So this actually, the intercluster medium lags in a merger. So these dark matter cores will go through, but the gas will lag a little bit. And there will be shocks and other phenomena in this intercluster medium that become visible in your different bands. So these shocks are visible in radio. They are also visible in X-rays, but given that the electron densities are very low here for the thermal electrons, the X-ray detection of shocks at the outskirts of clusters are very difficult. But radio bands provide you that facility, because electrons are reaccelerated at shocks, and you can trace these shocks in radio bands. And here, just to mention that these are the most energetic collisions you can imagine in the universe, and the gravitational potential energy that is dissipated in these phenomena is of the order of 10 to 63, 10 to 64 ergs. So here I want to, okay, I don't know why this is not visible. Anyway, I don't know. Is this? Yeah, I don't know. This is not visible. Okay, anyway. So at the end, I want to mention one more phenomenon. So I told you about the intracluster medium affecting the galaxies and these properties. So they also affect the radio galaxies drastically. So this is one example of an active radio galaxy where there is a core and jets and lobes, etc., and there is surrounding intracluster medium. But this radio galaxy won't be active all the time, depending on how the accretion happens at the central supermassive black hole. This can stop, leading to basically just passive evolution. The jets don't have any fresh input and they can evolve passively. So this is an example of such a passively evolving galaxy which has undergone modification due to the presence of intracluster medium disturbances. So what I have shown here is in green, these greenish white are the galaxies. In the red, you can see the X-ray emission, and in blue is the radio emission. And in synchrotron mechanism or synchrotron emission, you may have come across the lifetime, synchrotron lifetime. Synchrotron lifetime is very short, of the order of 1 million to 10 million years. So what happens is that the spectrum steepens very soon, and what that means is that it becomes difficult for detecting a particular emission at higher frequencies as compared to lower frequencies, because of the way the energy is lost. So the energy loss is proportional to the square of the energy of electrons and the magnetic field square. So higher energy electrons lose their energy faster, and this can be translated to saying that your high frequency emission will go down faster than your low frequency emission. So this is what has happened here, and what is blinking is basically the emission detected in 2 radio bands of the GMRT. So this little filamentary thing is actually a detection of that source at 1.4 gigahertz as compared to this large cloud that we detect at 330 megahertz. So as you go to lower and lower frequencies, even within the bands that GMRT observes, the view of your galaxies can change drastically. And this is one example where this old radio galaxy has been drastically modified and distorted by the motion in the intracluster medium. So another last thing I want to mention is about superclusters. So galaxy clusters are not just, they are not standalone entities. Everything is basically affected by each other in the universe. So there are regions in the universe where there is an overdensity on even larger scale than just a galaxy cluster scale, and such regions can evolve into superclusters. So this is one such region, the most nearby supercluster, most largest nearby supercluster called the Shapley supercluster. And what is shown is a very large region of sky, All these red points, red diffuse blobs here are the X-ray emission. And what is encompassing this bluish huge cloud is actually the detection of this whole patch. It's the detection of the intergalactic medium on these large scales in using the Sunyaev-Zeldovich effect. This is a Planck detection of this core of the supercluster. So now one of the open challenges is whether, excuse me, whether there is magnetic field on such large scales. And this is something open for the radio telescopes. Sorry, I think I muted. Yeah. Sorry, I had a little bit of cough. Yeah, so at the end, I want to just show you this this view of galaxy clusters across the electromagnetic spectrum. So going through the highest frequencies like the gamma rays all the way up to radio, we can see a different view of the galaxy cluster. Sorry, excuse me. We can see a different view of galaxy clusters, and each of this view is actually telling us a little more about the physical condition of the baryonic matter, the dark matter in these systems. So I will actually stop here. So I'll upload this presentation in some area, and there you can look at the reading material if any of you are interested in pursuing or reading about these phenomena in more detail. So I can take a few questions if we have time. Yeah, I'll stop here. Thank you.
Am I audible? Hello? Yeah. So, ma'am, in the beginning, you showed the simulations of galaxy clusters, and there the galaxy clusters are formed because of the initial density perturbation. And the simulation time is around the current age of the universe. And we saw there are some filaments connecting the galaxy clusters. But what would happen if we let the simulation fall? Like,
Sorry, what will happen is?
what will happen to this filament that connects the galaxy clusters? Like, will they break apart, or the connection still remains?
So it will eventually get thinner and thinner because the galaxies are basically falling towards the clusters. So the gravity will decide how the mass will be eventually distributed, and just like the voids have formed and they are increasing in size. So basically the large scale structure, as you see, there are filaments and the nodes are clusters, but then there are also voids. So these voids are not totally empty. There are also very, the galaxy numbers are very sparse. So you will have to go large distances in the voids to find a galaxy, etc. But they are not completely empty. So these filaments will also eventually most of the galaxies will probably fall into these clusters, but they'll continue to become, let's say, more sparser in their content. So that is how voids are also evolving.
Okay.
I have a question. Does every galactic nucleus has a supermassive black hole?
So we know that most massive galaxies have a central supermassive black hole, just like our galaxy and galaxies like the Milky Way or typical galaxies. They are likely to have a supermassive black hole. In the dwarf galaxies or in smaller galaxies, some of the irregular galaxies, etc., there may or may not be a supermassive black hole. But as far as we know from the evidence of the emission, AGN like emission from the centers of galaxies, those galaxies definitely contain a supermassive black hole.
Okay. Can a galaxy that was dragged into a cluster get out of it?
So, so getting out of galaxy clusters will be difficult unless it was on a, let's say, on a peripheral orbit such that it didn't actually completely fall in but grazed the galaxy cluster and went its path. But really, to come out of a galaxy cluster, you need to provide it something needs to provide it with energy to really escape the gravity of galaxy cluster. Otherwise, it will most likely stay bound to the galaxy cluster and evolve there. But initially, if it was not really falling or it was on a peripheral orbit, it may also just pass the galaxy cluster and not get bound over there. It depends on the initial energy of the galaxy.
Thank you.
You're welcome.
Just to add to Ruta's answer on the black holes, there were reports a few years ago of massive black holes in dwarf galaxies as well. The estimates of mass were smaller than the supermassive black holes in the giant ellipticals or quasars, and they were also not located right in the center, several of them. So it's possible that these black hole systems or black holes over there are still evolving. So anything with a bulge should have a black hole ideally.
Yeah.
Hi, Ruta.
Yeah.
So in one of the slides, you have shown that the galaxies are traveling. Like example, you gave the example of jellyfish, and after that, so in the radio image, you have shown there are jets which are like going outside. So that is due to the gravity which is dragging at the center of galaxy cluster, or that could be the interstellar medium also. The wind or the interstellar wind may be causing that.
Yeah, even interstellar wind can cause some distortion of the jets. So depends on what scales the distortion is. So if the distortion has happened within the extent of the optical galaxy, it could be originating because of the local medium. But in the cases of like these elliptical galaxies, the interstellar medium is basically so the BCG is just surrounded by this cluster core. So the it is surrounded by quite a dense medium. So in case of cluster galaxies in general, so in BCGs, since they are at the cluster, let's say the potential minimum of the potential, they don't move much. So the distortions are not very common in BCGs. So the distortions are on a larger scale where the cluster medium starts to distort the jets. But in other galaxies, like the one I showed, 3C129, it is actually moving in the cluster, is not the BCG, and it is infalling. So the jets are distorted on the scales where the ICM starts to basically change the shape rather than the interstellar But even phenomena like precession of the black hole, that can also jets can precess, and some of the features in radio galaxies, maybe in the radio galaxy related lecture, there will be some emphasis on that part. So those can cause some distortions, but the intra-cluster medium causes the jets to bend on the let's say few kiloparsec or tens of kiloparsec scales.
So maybe they are in cluster, and due to the collision, they might be distorted due to the shock waves. That also be a possibility.
Yes, definitely. So the thing is that when you have these shocks in the intracluster medium are very weak. So so they affect the lobes or the the part of the radio galaxies which are much thinner, as they basically go away from the galaxy. You'll find that the pressure is less and they can be easily distorted by the shock like phenomena. So this has been observed that a radio galaxy has been proposed to be passing through a shock, and the portion of the lobes has even undergone reacceleration. So one would expect that the core and the jets have a spectral index which is mostly flat because it is being continuously fed, and it will gradually steepen as you go away from the core. So there is basically this shock can distort, either compress, so there can be adiabatic compression and you can see a boosted synchrotron emission from there, or there can be direct reacceleration of these electrons, and you may find that after some point where you expect the steepening to continue, there is a region, or the remaining region which has passed through the shock has flatter spectral index. So such trends in spectral indices are seen in a couple of radio galaxies in galaxy clusters, and people have proposed that the shocks have resulted in that reacceleration. These examples are just a few, or you need multi-frequency, observations to confirm these kind of trends. So they're not very common, but they may be common if one looks at many such galaxies. Probably many more such candidates will come up.
Can I ask a naive question?
Yeah.
When the clusters merge, many cases have been seen. Do we expect the merged version to be more bound?
More bound in.
It should be more tightly bound because now you essentially increase the mass, haven't changed the velocities of the members, right? Now it should feel more gravity.
Yeah. So one can just look at, let's say, the clusters have formed through mergers, meaning, so if you look at clusters of different masses,
yeah,
one may be able to tell from the, let's say, the profiles of the intercluster medium. So definitely between groups and clusters, clusters are more tightly bound than groups.
Yeah, what I meant is if two clusters merge, then the resultant now bigger cluster should be more bound than.
Yeah,
I'm
but
just
it will
comparing the
need some
member
time.
velocities, which we are not going to change because they are not going to interact, with each other in any way except to respond to the common gravity, right?
Yeah. Yeah, so I think the initial velocity of the merger will uh, will decide how long it takes for the cluster to relax, um, and then one can notice this difference because of the mass now.
So have
Yeah,
people
maybe.
asked the question about the non-interaction of dark matter or whatever? Uh, if in the merger, is there any traces or suggestions of signs of any interaction or behavior of the dark matter that might manifest itself in some
Yeah,
other way, if at all it behaves like any other expectation, like partly like baryons and so on.
yeah. So people have put bounds on the dark matter particle masses by studying cluster mergers. So what they do is you can use gravitational lensing. So people use weak lensing often to trace the mass distribution. So you measure the lag between the galaxies and the dark matter cores,
Okay. Mm-hmm.
and then you can put bounds on the dark matter interaction cross section. Sorry, that.
So does so far it appears like they just go through each other, I mean, without interacting, or is there anything
Yes,
interaction?
yes. So it is just a limit so far. I think they are among the strongest limits actually.
Yeah, thanks.
I have one more question.
Yeah, go ahead.
Yeah. So, like, if we let this, I mean, if we let the entire universe evolve over time, you said that there might be voids and the galaxy clusters may become more and more compact. So we know that the universe expansion is driven by dark energy. So, like, after the universe evolve for a sufficient amount of time, when there will be massive galaxy clusters, uh, so will there exist a quasi-static state where the gravitational attraction due to these galaxy clusters will counteract the negative pressure?
Mm, I don't know the answer. Mm, so one can evolve the simulations in the limits of the, you know, the physics that we know, or even the cosmology that we know. So, so the picture that we know from simulations is basically the picture from what physics one has put in that simulation. So within this known physics and cosmology, one can see what happens eventually to a universe if you keep it um, evolving just like one has evolved. Yeah. But I don't have an answer for your question, like what exactly. Uh, I don't know if someone wants to add, maybe.
Just a follow-up question to that. So,
Hmm.
so does the negative pressure is constantly evolving or is it constant?
Hmm. No, I don't have a one-line answer for that. So the expansion of the universe, basically, it is also accelerated expansion.
Yes.
Yeah. So yeah. So from that, one may infer the dark energy, but I'm not very right now. I don't know the answer one line as such.
Okay, ma'am.
So most of our evidence for the cosmology, or how our universe is has come from, let's say, the supernovae data and so on. So there one has enough evidence to say that universe is expanding, and the expansion is accelerated expansion, and one will have to check the details as to what is the actual implication for the dark energy, etc. Yeah.
Okay, ma'am. Thank you.
I think to naively understand it, I mean, a gravitationally bound system would be a gravitationally bound system, but the space-time matrix is expanding, and in more recent times, it's accelerating. So that acceleration will happen, but it is the clusters or like the stars or stellar systems, they are gravitationally bound systems which will continue to be gravitationally bound, but they are embedded in a space-time matrix which is actually expanding. So that is one sort of simple way of looking at it.
Okay.
One more question about clusters. Well, so if we have a group of galaxies together, I mean, could we have a group of galaxies, but they are not really bounded into a cluster? Like they are close to each other, but not in a cluster. How can you differentiate?
So one can look at so what people do is they look at the velocity dispersions of the population of galaxies, and that can tell if the orbits or basically this is a bound system or it is just a chance, let's say, uh, a chance observation of these galaxies together. So if we measure the velocities of the galaxies, so in galaxy clusters, for example, where these are bound systems, you will find that if you plot the velocities of the radial velocities, which are velocities along line of sight that we can measure, and if you plot them, they look like a Gaussian distribution, or no. In a bound system, you will expect the particles to have a certain velocity dispersion, certain velocity distribution, and if they are not bound, they will not show this kind of a distribution. But if there are very few galaxies, then it may be one may need to find some other probes to see if they are bound or not. This you can do, the velocity dispersion thing you can do if there are a large number of galaxies.
I see. About Einstein rings, you know, that distortion in the imagery when you want to observe an object that's behind a cluster. So can we actually do something image-wise to remove that distortion, or we can just observe it with the Einstein ring?
So in gravitational lensing, you will get different images distorted in different ways, and yeah, I don't know, one does model the gravitational potential and can predict how the actual object would look like if you remove the effect of the distortion. So if you basically, if you know how the mass distribution is and can, from the different images that you obtain, the distorted images, you can construct the let's say the geometry of the system, and then then try to see how the undistorted object would look like.
Thank you.
Ma'am, I had a question.
Yeah.
So we know that spiral galaxies are often the young galaxies and they later evolve into elliptical ones. So how does a spiral galaxy exactly evolve into an elliptical galaxy? Is it just by collision with some other galaxy, or can they evolve on their own? And does an elliptical galaxy ever evolve into a spiral galaxy?
So yeah, so when these galaxies fall into the cluster, they lose most of their gas and Basically, that is why there is then no new star formation, and then what you get is a system with just old stars. And if such systems merge, then uh, a galaxy like an elliptical galaxy may be formed. But I don't know if maybe Sykes can add based on any galaxy evolution aspect.
Yeah, if you look at, for example, the distribution of colors and mass of galaxies, you'll find that the red ellipticals are generally red in color and they're more massive. Whereas the early types, the spirals are more blue in color and they are less massive. But on the other hand, you find a lot of interlopers. So general sort of one way of forming ellipticals is by mergers of spirals, but whether ellipticals are formed on their own by collapse of asymmetric collapse of a cloud is also a possibility. But the fact that spirals can merge to form ellipticals is numerically predicted, as well as observationally. There are evidences of galaxies combining, which are in various stages of coalescence, including neutral hydrogen mapping, to show that that is a viable process. On the other hand, for example, suppose you had a spiral, which is not actually combined together, then and there is no new gas coming in. Then you could also have spirals which, just bright young stars die off and look reddish in color. Or you can have ellipticals which may have acquired gas from its vicinity in a cluster, and where sort of some kind of a disc-like structure, not exactly the bright spiral arms that you see in the classic spirals, they have formed. So you have interlopers, but basically the broad ideas of which Ruta outlined is what it is. So it is these interlopers which appear in what is called the Green Valley when you look at the color and mass diagrams from hundreds of thousands of galaxies which have been plotted, particularly from the Sloan Digital Sky Survey, which has very large numbers of galaxies. So different processes are possible, but what Ruta talked about are processes which are viable and probably, and there's both observational and theoretical evidence that that is probably the case in many examples.
Okay, thank you, sir.
So we'll probably take a gallery shot as we all do for all the lectures.